Okay. So, picking up where we left off. So, hopefully this looks kind of familiar. Remember, Edwin Hubble, he was good about actually finding the distance to the Andromeda Galaxy, which kind of put things in perspective. It's not just a nebula within our own galaxy. It's like an island of stars, and the reason it looks so wispy is because it's so far away. So the concept of a galaxy kind of fell into place with Edwin Hubble. And then what he did is he made a scatter plot. Scientists are always doing that. And so those little dots all represent, we talked about on Friday, those little dots all represent galaxies. So the universe is expanding. We'll be talking more about that in dark energy in Unit 5. But the universe is actually, galaxies are, the expansion is accelerating. So actually, the farther away the galaxy, it was moving faster from us. So the farther away it was, its recessional velocity, its moving away velocity was even greater. So this h sub 0 actually is Hubble's constant. And I added a few things to this slide, so don't get too fretted about it. But when I got to thinking about that scatter plot, it has a nice straight line. If you're familiar with kind of a straight line on an XY plot, you actually can come up with the equation for a straight line, okay? And y is equal to mx plus b, where b is the y-intercept and m is the slope. So if you go back to the previous slide, actually h sub 0, Hubble's constant, is the slope. And so there's a really kind of a cool outcome of all of that. If you take what we call the inverse, or 1 over h0, you can actually backtrack to the age of the universe based upon Hubble's law, which was the plot we just saw. So I'm all about, some of you guys know in my physical science classes, I'm all about factor label. So actually, this right here website will kind of take you to kind of the inverse of h0, and actually that is velocity over distance, distance over velocity, how that kind of connects with factor label, coming up with the age, t, of our universe. And so I've done this on paper to convince myself. So bottom line, and actually this is on your test, it turns out that there's a little play in the h0, Hubble's constant, but it's about 13 to 15 billion years old, bottom line. There's more than just one way to estimate the age of our universe. And we'll be talking about the Big Bang in Unit 5. How long ago did that happen? 13 to 15 billion years ago, according to Hubble's law. So I will actually write that on this slide, because I don't think I clearly say it. Let me change to red. So 13 to 15 billion years old. Happy birthday, universe. Okay. So again, it kind of links into what we're going to be talking about in Unit 5, the Big Bang. But honestly, well, there's two things here, I guess. When we talk about the cosmological horizon, the way I look at it is, if it takes light a certain amount of time to get here, okay, and from an object that's sending us light. Let's say that object is 10 billion light years away, so it takes 10 billion years for that light to get to us. That's cool. Well, let's say that object is 20 billion light years away. Now, what I've just described is basically a distance that the universe hasn't been around 20 billion years for that light to get to us. Does that make sense? We kind of we bump up against what we call the cosmological horizon. I mean, at some point, the universe hasn't been around long enough for that light to get to us. There is a limit to what we can see from our perspective, and it's just inherent in the way things work. Okay, but with that said, we don't see that there's any edge to our universe, which is kind of cool too. So we don't see that there's any edge to our universe. And so this balloon actually is trying to kind of depict the expanding universe. And so on the outside of this balloon, we have these A, B, C, and D kind of perhaps galaxies all spreading apart. So it seems like the universe is kind of lumpy. I mean, we have spaces in the universe where it's a vacuum. There's no atoms, no nothing, okay? But if we step outside, and then we have places like the Earth where we have all sorts of atoms, right? In our solar system, all sorts of atoms. But if we step outside and kind of take a bird's eye view, the fabric of how matter is distributed through the universe is really pretty homogeneous, really pretty kind of constant. So here's kind of a thought. Okay, it can get really kind of mind-boggling. So what you're looking at is this is the Milky Way right here. This is us, okay? And this is another galaxy. And in another galaxy far, far away, they had some sort of event. Maybe a star within that other galaxy blew up, supernova, type 1A or 2, your pick, okay? So let's say that event happened 400 million years ago. Well, right now, 400 million years, or actually I can't really put a time on it, but all galaxies, most galaxies, are moving away from us. So I'm kind of showing you that recessional motion there, okay, after some sort of time. But the deal is when are we going to see that nova, or when are we going to see that supernova event? When are we going to get that light? And when we finally do get that light, what is it light from? It's not light. We know that when we see that supernova event, if the thing's like 400 million light years from us, okay, we know that it didn't just happen. So now that, let's see if I have another built here. Now that galaxy is not here, but now that galaxy is here. But the light that we see actually was as if when it was back here, because it took, I know. It has to do with kind of a moving target, okay, and the fact that it takes light so long to get to us, or a certain discrete amount of time for light to travel that distance. So this is all to say that, and I'm glad that they do, instead of trying to figure out kind of the ins and outs of where that object or where that galaxy is now, what they kind of make it simple. They just kind of go with what we call look back time. Okay, so it's just kind of mind-boggling, kind of disconcerting actually, but we keep it simple. Okay, so what we see, we say that's where it is, even though we know it's not. Okay. So we have another type of redshift, like we really need another type of redshift. And this redshift actually has to do with the fabric of space and time that is getting larger. Space and time is expanding. It has been ever since the singularity that associated with our Big Bang unfolded. So with the expansion of the fabric of space and time, we have another elongating wavelengths, okay? So this is called the cosmological redshift, and it's different than the redshift associated with a galaxy because it's moving, the Doppler effect. It's a different one. Okay, so back to galaxies. This looks like it might have been taken by the Hubble Space Telescope. Remember, it was kind of a rush when they took a place in the sky that there was nothing. And they looked deeper and deeper and deeper. And there's these galaxies out there. So one of the things I'm going to emphasize is that if we are looking, how do I say this? It takes light, again, I said just a minute ago, it takes light a certain amount of time to get to us. So we actually are seeing baby pictures of those galaxies. Farther away they are, the more the baby picture that we're seeing. So they think that we were able to see light from the universe. The universe kind of calmed down about 800,000 years after the Big Bang. So actually, these are some very distant galaxies, and since they're very distant galaxies, these are baby pictures of galaxies. And they look a little irregular, don't they? Okay. So these are actually a set of galaxies going from baby pictures up to more current pictures of, we said, the 3 types of galaxies: elliptical galaxies, spirals, and barred spirals. Yeah. Okay, so they just kind of get a little bit more defined. So in your test, when I ask you, how can we kind of see how galaxies kind of evolve, kind of start baby pictures to newer pictures, it goes back to one of the things that I think you guys know, is that if we look back, if we look, excuse me, not back, if we look far away, that is a baby picture. And if we look kind of close up, that is a recent picture. So we kind of have a string of evolution of galaxies. Those are spirals, and these are irregulars. Now we're going to see actually irregulars. To me, sometimes irregulars kind of they lack definition because they're babies. Sometimes irregulars lack definition because they've been playing Smash 'em Up Derby with another galaxy. Okay. So I'm going to introduce a term called proto-galactic cloud. And we've talked about how a lot of clouds from a cloud, you can bud a star, okay? And actually, this is a cloud that has enough stuff in it to basically have a lot of stars born into it, a whole galaxy of stars, okay? But it's kind of similar to what we've been talking about. You kind of see the fragmentation here. Okay, so this is kind of over time. All right, so like a prototype, proto-galactic clouds, the thing that ultimately is going to spawn a galaxy. And at the time of our universe being in its infancy, the only elements they had a lot of hydrogen, some helium, and a smidgen of lithium and beryllium. And actually, those are kind of the next ones on the periodic table. So these protogalactic clouds were chock full of hydrogen and helium to form the first stars. So I'm going to kind of talk about how do we get our elliptical galaxies, which are kind of like blobs, and how do we get our pretty-looking spirals, the barred spirals and the spirals. And what it comes down to in a little bit is angular momentum. So if there is a certain amount of spin, we can have angular momentum. No spin, no conservation of angular momentum. So kind of the 2 types are here. There's a 3rd type, actually. But to me, spirals and barred spirals, they have some things in common. They have a disk component clearly to them, and they have the arms, whether they're a spiral or a barred spiral. Ellipticals, like I said, they're kind of, I think they have a lot of spheroidal, I'm getting better at pronouncing that, component to them, elliptical galaxies of stars. So here again is Hubble's tuning fork diagram, where we have our ellipticals and we have our 2 types of spirals. And our ellipticals, the spheroidal component dominates. And if I go ahead and build this, both the spirals and barred spirals, you definitely have like I was saying, it kind of comes down to spin. So what you're looking at here are 2 tracks. The top track actually is no spin, and the bottom track it's got a significant amount of spin. Okay, so these will give you your ellipticals, and these will give you your spirals and your barred spirals. It's funny, barred spirals is SB instead of BS, but does that make sense? So the spin actually kind of conserves a disk component or creates a disk component. And that's kind of the size of it. But there is one other thing. If you don't have spin, okay, not only do you not get a disk component, okay, so this is no spin, but also when it comes to kind of your stars and their proximity, your stars are a lot closer together. That almost makes sense to me. When they study elliptical galaxies, they're seeing that the stars are kind of close to each other. I'll buy that. So elliptical galaxies, actually there are kind of, a subgroup of elliptical galaxies that are composed of just kind of old stars. Okay, we said that actually M-type stars are generally red, and M-type stars are low mass, and they're like the Energizer Bunny. The low mass stars last a long time. So actually some of our galaxies contain these older low mass stars, elliptical galaxies. So I said irregulars can be irregular galaxies. They're not one of the three main types of galaxies, in my book anyway. But irregular galaxies can be irregular because they're babies, or they can be irregular because they had some interaction with another galaxy. This is kind of a famous pair of galaxies caught in action, where you are looking at it here in the visible region, okay, and here you're switching wavelengths, so you can kind of actually see clearly see the mass being exchanged. So I chose, sometimes it's hard to make up your test because this seems kind of like a random fact. But if we consider that this is what the galaxy looked like, excuse me, the universe, this is what the universe looked like early on, and then we have this expansion, fragmentation to go ahead and create a galaxy of stars. Actually, when our universe was smaller, it allowed for more interactions between the galaxies because they were closer together. So again, kind of looking at the evolution of galaxies. So actually, now this is saying not only can galaxies look irregular like this because they're young, but because they were young, they were more likely to be interacting with other galaxies. I like the word disturbed. So one, I guess, a positive thing that can happen when galaxies interact is actually they can prompt the birthing of stars in their collisions. That's a good thing. This is not an animation, but kind of a series of photos kind of showing you one possible interaction between stars. I could play this for you, and actually it's a video. I think it's on my set of videos for this chapter. But this talks about the Andromeda Galaxy and its dance with the Milky Way galaxy. Yeah. And I've listened to it recently, and actually in 4 billion years, which is kind of cool because it kind of almost coincides with the sun leaving the main sequence. In about 4 billion years, the Andromeda Galaxy of stars, which is a little bit bigger than the Milky Way galaxy of stars, actually are going to do this. Okay. And then according to, and I don't know if they've changed have any new information to update their model, but according to that video, it's going to be kind of over time, but I should say our star is not going to collide with any other star. But over time, when things settle down, our nighttime sky will look different. Okay, we'll have different miscellaneous stars, but honestly, the disk of now the Andromeda Galaxy is going to merge with the Milky Way galaxy, so the disk of our galaxy is going to look different. Okay, so not all galaxies are moving away from us. Most of them are. So this actually is a cluster of galaxies. It's a cluster of elliptical galaxies. And we're going to talk more about how galaxies are organized, and that's kind of the first stage of being organized into a galaxy cluster. And oftentimes elliptical galaxies have this humongous family. Okay? So those are not individual stars, those are individual galaxies. And the cool thing is, that's what they look like, that's what the sky looks like in visible light. But this is what that same field of view looks like in a different wavelength. Okay, so you kind of get a sense for things that are hiding in some of that muck. The yellow, I guess it would be, are dense little cores of galaxies. Kind of creepy. So this is just an individual galaxy. And starburst galaxy is not one of the main types of galaxies, but it is kind of a way to generally describe galaxies. And I think they get their name starburst from kind of like a kind of quickly group of stars are born. So what you're looking at here is This would be the disk of the galaxy, and these would be kind of jets of material kind of going on either side of the center of the galaxy. Most galaxies, we think, harbor in their nucleus, the nucleus of a galaxy, a black hole. So actually, that's one of the last topics I need to talk about. I'll just put BH here for black hole, is the fact that these black holes in the centers of galaxies sometimes are active. It almost looks like that's kind of a little bit of activity going on there. Okay, so this is that same starburst example of a starburst galaxy. This is the disk, and kind of you see the region in the halo region above and below the disk where there's material being ejected. So the last topic we need to talk about are quasars. And I think on one of the videos we watched in here, he talked about quasars. They're the quasi-stellar objects, okay? And quasars are associated with the heart or the nucleus of a galaxy. And they are very energetic. Quasars, honestly, in the heart of a galaxy, this energetic event, if we are in the line of the energy, and usually it's like, comes out the halo region, okay? So here's the disk, okay? Here's the center of the galaxy, and here's the quasar. If we're in the side of that, we could be toast. We could be totally sterilized. Okay? A lot of energy. So, quasars, though, kind of historically, they're very energetic. And the other thing that they found out is they have a lot of redshift, which simply means that they are in a region of the universe, or associated with, a galaxy that has high recessional velocity. The greater the redshift, the faster it's moving away from us, and that means it must be farther. So this is an image of a quasar event, and your author's kind of drawn an attention to a galaxy that is being adversely affected. I think that's adversely affected by the quasar that's being emitted by another galaxy. Again, quasars come from the center of galaxies. And at the center of galaxies are black holes. So quasars actually are associated with black holes. So one of the things about a quasar event is it's not just energy just in one region, it's energy across the spectrum. Okay, so these are all different wavelengths that the quasar emits energy at. So kind of related to that, sometimes we see quasars because of the gas and dust that's in the way. It's good to go ahead and switch to a wavelength or band of energy that comes through the clouds, and that would be radio. So sometimes quasars seem subdued, but actually they're still happening. And they seem subdued because there's gas and dust in the way. Okay, so quasars kind of eject material, energy at a right angle to the disk. So this is the way I think of it. So this would be our black hole. Okay, and the disk of this galaxy actually is there. Now we talked about this before. I think somebody said, well, how can this energy get out of a black hole? And I think I answered it something like, actually, that energy is created by the commotion of a black hole, but it is outside the event horizon. Otherwise, you're right, it would not get out. So that's sort of what we have going on with the quasar. So this is showing you a series, 1991 to, that's 6 years apart. Okay, just showing you kind of the emission of matter and energy from a quasar. And this goes back to radio galaxies. You know, if somebody says, oh, that's a radio galaxy, you're like, oh, well, that must have something to do with quasars. And I'm actually kind of primarily in the radio wavelength seeing it, even though quasars are energetic, all sorts of wavelengths. It's just subdued from the gas and dust. Okay, so it almost seems a little backwards. I talked about quasars, and I already told you that from my understanding, that crazy energetic event is associated with a black hole in the center of a galaxy. So the Milky Way galaxy is not active. The Milky Way galaxy, scientists got kind of excited maybe, gosh, has it been a year or so? Because actually a star is getting closer to Sagittarius A star, okay, orbiting, and its trajectory is that actually it's an accretion disk of the supermassive black hole, and so it can be torn apart, and our supermassive black hole can eat it. Okay, so kind of what I'm describing here in a small scale with our Milky Way galaxy is kind of the activity when we talk about a galaxy being active. Okay, but other galaxies are much more active than that. Okay, basically it's what we call almost a feeding frenzy. Okay, an accretion disk, just like we've talked about accretion disks before, but now matter actually is swirling toward it's called a supermassive black hole in the center of a galaxy. Okay, and when they do that, it can create what we call a quasar. So I used to include it more in my notes, and I think I emphasized this the other day. But there are different types of black holes. The black hole in the center of any galaxy is called a supermassive black hole. We talked about, I'll call it SN type 2. Okay, remember that's a massive star that goes out, blows up, and actually that can create a neutron star or a black hole. The black hole it might create is called a stellar black hole. Okay, so a couple different types of black holes.
Wait, can you? Mr. Evans kind of distracted with the voice. Could you say that one more time? The last part about the type.
Sure.
Different types of
there's two types of supernova. That's the SN part.
Okay.
And the supernova we talked about in the last unit was when a star that is more massive than 8 solar masses, okay, when it goes out, you either get a black hole or a neutron star.
Oh, okay.
Yeah. Yeah. And then we call that, if that type of black hole is called a stellar black hole because it came from a star.
Okay.
You're welcome. So this is just kind of trying to convince you that kind of the commotion that occurs in the accretion disk around a supermassive black hole can actually create the energy that we see in the form of a quasar. I'm convinced. Okay, and again, this is kind of showing you what I've, tried to kind of introduce early on, where this actually is the disk of the galaxy. Okay, and so in the vicinity of the black hole is that accretion disk where matter is kind of queuing to fall into the black hole, never to be seen again. So I do like this one where actually you can see the event horizon, so that's a good thing. You guys see that little event horizon? Don't go beyond the event horizon. It's like when you go swimming and your parents say, don't go past that rope. You won't come back. So this slide might look familiar. It's actually each one of those kind of little sets of balls are showing you where a star was over a period of, gosh, I think like 15 years. And it's tracking the motion of the stars that allowed us to get to the mass of the object in the center of our galaxy. Okay, so this actually is Sagittarius A star. Okay, so Sagittarius A star is our supermassive black hole. Supermassive. Sounds like something a little kid would come up with. That's supermassive. Okay. So, honestly then, it's probably not so surprising that we can look at other galaxies And to kind of understand what sort of mass is in the center of the other galaxies, we need to look at how the stars are orbiting that mass. And this is kind of a neat little trick. It's saying, actually, if you're kind of looking at that galaxy kind of edge on, you'll see a blue shift when the star is moving towards you, and you'll see a red shift when the star is moving away from you. And then you can get to speed. And so once you know speed around the supermassive black holes and other galaxies, then you can actually go ahead and get to the mass. And it's like, oh gosh, that mass, that small of area, ooh, you're talking black hole. Okay, so it's very similar. So like I've said, I kind of let this cat out of the bag a long time ago. Most galaxies we think have a black hole in their center. And we think black holes, or scientists think that black holes were important in the development of a galaxy of stars. But like this says, the Milky Way is generally inactive, okay? But we think that most galaxies have gone through their active quasar sort of stage. So the last slide, actually each one of these dots is a black hole. And so they are, again, a scatter plot, kind of trying to link how big, or sorry, not big, but how massive is the central bulge of a galaxy to actually the mass of the black hole that's hiding in the bulge. Okay, so here's a galaxy, here's the disk, okay, here's the bulge, here's the black hole. So it kind of makes sense that the bigger the bulge, the more massive the black hole that it's harboring. Gotta love those scientists and their scatter plots. Okay. So we have a few minutes until noonish. So anybody who wants to come join me down in the Chem Lab can at that time. And we'll go to the Success Center.